there was also the prime divisibility property, which I didn't do in this class. Would you like to revisit that for 5 minutes or just move on?
Revisit.
Revisit it.
Yeah,
Let's take a quote. Raise your hand if you would like to revisit. That's 4 people. Raise your hand if you want to move on.
Was it 4 people?
More than that. Okay, I guess we're moving on. Sorry. Okay.
I'm one of the 3 million voters.
What I am not going to give you a vote on is I do want to like for a very short number of minutes, like 5. I want to revisit this proof on the infinitude of the primes because I heard that sigh. Okay, we did this proof, Alice, and it was decently kind of good, except it was a little bit wishy-washy and vague, and in fact, when I discovered over the weekend when I was just sitting in like weird parks in New York City hanging out with hipsters and their babies and doing prime number proofs, is that these proofs could get kind of hard, and you can sort of think you know what you're talking about, but if you're just like, wait, let me be a little bit more precise about this, then suddenly you realize, oh my god, I have no idea what I'm talking about. This doesn't make any sense at all. This is an argument for rigor. Okay. Here's what we did last class. Here's your 1-minute recap of what we did last class. We said we wanted to prove that the primes are infinite, right? So we said, Tibur, are you okay? Laptop good? Yeah. Okay, let the record show for the internet that I did not break the child's laptop. Okay, good. Can you turn it off now? Okay, good. Alright, so, how old are you, Tibur? 17, yeah. Good. Alright. Yeah. So what we said is suppose the set of primes is finite. And then what we said is, okay, so that means let it be this set, like P1, P2, etc., up to like Pn, right? And then what we said is, okay, well, no, man, that can't be. So this was like a proof by contradiction, right? This is how I advertised it, at least. And I said, okay, well, you know what? There's this number q, and this number q is p1, p2, all the way up to pn, the product of all those plus 1. And then we argued, in a technically accurate way, that q cannot be in this set P. Furthermore, we argued that, that P of k cannot divide q for any of the pk and p. And then, all right. So now I think when this happened in class, I said some crap that was like sort of vague, possibly wrong. I said when I said that q couldn't be in p, what did I conclude from this? I think I said that q is prime. No,
not prime.
No, I think I said composite.
Yeah.
Yeah, I think I said that q is composite. And then I made some hand-wavy argument and I said some shit that made no sense. I just decided that that's just like not true. It's just not true that q is composite.
How?
Because
all numbers that aren't prime are composite.
For example.
Yeah.
Q is not prime. So the set of all
Yeah,
numbers
but okay, but
Isn't it just by like linear division that q? No, if it's prime.
right. But it's just not. That isn't what the definition of prime is. Prime is prime. No, this is you guys bought my crap story.
No.
Last class.
Wait, if q is prime, then it's in the set.
Yeah.
So q is not prime.
Yeah.
No, if q is prime, then when we made the set, we would...
You're like q is greater than everything in that set.
Yeah.
So it's not in the set.
Yeah, I agree.
Like everything that's
it's not
prime
in the set. I wrote this down.
Yeah.
So I'm open-minded to decide that I'm wrong again.
I
So I'm okay with this. We all agree that q is not in P.
Yes.
100% agree.
Yes.
But P has all of the primes.
This claim I claim doesn't hold. You just can't say that q is composite if it's not in
Yes,
P.
wait.
Wait, if you define composite as not
Just
prime,
say that P is the set of all primes.
It's like...
No, but no, yeah. Isn't Q
It's like
composite under your assumption?
Exactly. Yes.
Yes.
Isn't Q
Yes.
composite under your assumption?
Yes. Under your assumption.
Yeah,
Okay,
we call
under
it
your
like-
assumption, everything is
How?
true.
What?
So you agree with them?
Yes. No, but then you show by your construction
He's
of
not
Q
here.
that
I
Q is-
haven't seen
Wait,
him.
because you
in
wanna
class
make a
math. If you find him, let
contradiction.
me know where he is.
No, so Q's composite under your assumption, right?
Yeah.
What do you need to demonstrate by your
I
construction?
think you
of
guys
Q?
are using Q as composite as a synonym for Q is not in P.
Yes.
Yeah.
Yes.
So why don't you just say Q is not in P? And then
Yeah.
we're all happy.
Okay.
Alright.
Okay.
And then if we reach
Alright.
a number, Q is.
No, wait, I think I am maybe going somewhere with this. Maybe not. I can't promise anything. This is a free public education you're getting. Don't complain. All right. So then, I don't know. I threw that. Okay. So then I showed that P doesn't divide. That none of these primes divide Q, right? So if none of these primes divide Q, then what can I say? Then what do I say?
I guess we never tried. Well,
What's prime?
There's has to be Q. Well,
I don't know about that.
Wait, why not?
there's has to be another
It's
prime.
Well, like, there must be a prime that
divides.
Yeah, well, now we have patched this up because we went through this rigorous proof, taking an entire board, doing it 3 different ways,
Yeah.
that every composite number has a prime factor. But I actually just like straight up don't know whether Q is prime or composite.
Yeah.
And it isn't in general one of those two, as we saw last class, right? Product of the primes plus 1 could be prime or composite. So like, I think my proof was crap last class. I really think it was. Now you agree with me that my proof was crap?
Well, I think that
Because I'm not sure where the contradiction is. Like, where's the contradiction
But if
exactly?
you assume an assumption that's false, then Q is obviously both prime and composite, because you're now in a world where there's a contradiction, so everything's true.
Assuming things are false.
No, but I have. Wait, no. I know that Q's not in P. I don't know. I find this to be vague. I tried to make this more precise, and I decided that it doesn't. No, I agree that if it's composite, it has a prime factor. And these, right? So I guess by contrapositive, it's like.
Critique.
Hold on, wait.
This is
Critique.
smart.
It's like really easy to fix. It's like you just use proof number 3, right? There's has to
Yeah.
be some prime dividing it, but like you don't know the
Yeah.
primes in P divided, so there has to be another prime outside of P.
Yeah.
Yeah, exactly.
That's what
Yeah.
Wait, you know that you can't divide it, right?
Yeah.
Yes. Yeah.
Yeah, it's a contradiction.
You know that none of the primes you.
No, all you know is that there's some prime that divides Q that's not
Not
in
in
P.
P.
Yes.
You don't know whether Q is that prime.
So you're saying by proof 3, I showed that every number has at least one prime factor, but this one just doesn't or something.
No,
Like,
how
it
would
does,
So
it's just not
It
in
does.
P.
It does,
just
but
not-
not in P.
Yeah.
Okay. So now we conclude. I'm being very. I think I'm right, but I'm being maybe like a little bit too annoying about this. What I agree with you is that Q has a prime factor. Of course, it has a prime factor. We just proved in the other board that it does, and that prime factor is not in P. Yeah.
That's the contradiction.
But no, where's the contradiction?
Because that's
Suppose
the
that
all
P was the
primes.
set of all primes.
Okay.
This
All
is
right.
exactly the
Yeah.
same thing.
I guess
Q
it's,
is composite.
I guess it's kind of okay. I don't know. No,
Or
it's
this
pretty
is
much
the
okay.
same as
I
saying
think
Q is
there's a better way of phrasing. So I read up on this proof. I like re-looked into Euclid's original proof, and there's like a whole commentary which says like that it's not actually a proof by contradiction, and it is often misunderstood as one. And I think it's much better to think of it not as a proof by contradiction. Instead, to just think of it as what Euclid is actually proving is that no finite set of primes is complete. I think this is the better logical way to understand the theorem. This is how I'm going to teach it from now on. Theorem, no finite set of primes is complete. Here's the argument. Take a set of primes. No
Okay,
claim
that's
to its
good.
completeness.
Yeah,
It's
okay,
just
that's
a
actually
set
good.
of primes. Claim this set cannot be complete. And the reason is, there's this number Q. If Q is prime, then it's missing, because it's not in the set. If Q is composite, it has a prime factor, but it's not any one of these. So again, you're missing a number. That, to me, is crystal clear, right? No set of primes can be complete, because
Yeah.
take the product of them all plus 1, and that number is either prime or composite. If it's prime, it's missing from the set, and if it's composite, it has a prime factor, which can't be any of those, so you also have one missing.
Wait, so then your set isn't complete. Isn't that like a contradiction?
Well, it's not a contradiction, because I haven't ever assumed anything. I've just taken an arbitrary set, and I've said this set is incomplete.
Oh, and you can take all sets of primes.
Yeah, and now, and actually, if you took logic, you'll know that that's much more of like a Euclid style proof, because Euclid doesn't even believe in like actual infinity. He believes only in potential infinity. And so you probably wouldn't find Euclid saying something like the set of primes is infinite, because what the hell does that even mean? To Euclid, the set of primes is sort of inexhaustible or something like that, right? In that he shows that given any finite set of them, you can sort of construct another one. And that
was that equivalent to being
yeah. Depends on kind of what exactly you mean when you say that the set is infinite. And saying that no finite set of them is complete is a kind of way of saying it's infinite. But I will not subject you to this, did the whole proof over again using Gosset's definition of infinite.
Which is?
He says a set is infinite if there exists a proper subset of it, of every size.
Wait, that's not
of every n.
Okay.
So this was his definition. S is infinite. S is infinite if and only if there is a subset Sn, a proper subset of S with the size of Sn being n.
I mean, I would think you would define it.
Wait, do you agree with that definition? Okay, and now if you really wanted to, but we won't, but maybe I'll talk about it for like 1 minute, you could prove that you can do this like Gosset style or whatever by sort of saying, you would do it by induction, right? You would say, okay, base case is n equals 1. Do you know of a proper subset of the primes of size 1?
29.
Yeah, how about we throw in just the number 29? I agree that this set is of size 1. Cool? Say cool.
Cool.
And also that it is a proper subset, because it's missing like 2. Because Josh decided to be 2. Okay. That's like the base case. And then the inductive step is to suppose that there is a set of primes of size n, or rather, that this is a subset of the primes, a proper subset, and also that it has size n, which I kind of like have there, right? Okay, and now what I must do, this is my inductive hypothesis, what I must do is now construct a proper subset of size n plus 1, and I can do that by kind of going through this argument again. Wait, don't fall asleep.
Michael Yin came in last place.
Give it to win it.
It's between 2 white guys.
God damn. Alex Ross.
No! And some guy named Matt Post from SHS, which I guess is like.
Oh my God! No!
Are those bad people?
Wait, if you think I don't think
Wait,
Alright.
his Twitter feed is like pretty cool. It's like talking about like Malala Yousafzai and like internationalism.
Okay, good. Democracy has been proven to be a failure again. Alright, good. Inductive hypothesis, so can I just wrap this? Are we done? Maybe we should just move on.
Yeah, we're done.
I mean, we're basically done, but okay, but even for the people who are very skeptical and don't care about this, I'll just say, add one more quick thing, which is, what we now do is, of course, we take Q, right? And we let Q be P1, P2, all the way up to Pn plus 1. And now we repeat this argument, right? That Q is either prime or has a prime factor not on this list. So whichever one of it that is, that's what you should set Pn plus 1 to. So you set Pn plus 1 to be like Q if Q is prime, and like the prime factor of Q, not on the list previously, if Q is composite. Is anyone with me? Okay. And if that's true, then there's this extra one. And now I throw that one in my set, and that set is still incomplete by doing this argument over again. I feel like we're good on this. Okay. So, good. Let's take a 1 minute break. Hit the off button. Let's take a 1 minute break to, should we call Michael Yin?